Welcome back to another video of our course Probability Theory. We are now starting to discover some new things which you might not have learned in the basic probability course, which are different kinds of convergence. So from your calculus class, you know that functions can converge in different senses. For example, pointwise, or uniform, or uniformly on compacts, and all these nice things. And in probability theory, we even have a bit more kinds of convergence, which are all important and which are connected. And that's the topic which we will start today. So let's start with the different kinds of convergence. And this is the overview. So we'll cover this in the next videos. So you see here that there are 1, 2, 3, 4 boxes which stand for 4 different kinds of convergence. Almost sure convergence you know from calculus, or if you have measure theory, that's the same as convergence almost everywhere. You do not know convergence probability, probably. LP convergence you might know from measure theory, and V convergence you might know if you have already attended a class in functional analysis. And so these 4 kinds of convergence, you cannot really say which is the strongest, but for example, you can say almost true convergence is stronger than convergence in probability, because you have the arrow here, which means from almost true convergence follows convergence in probability, and the back direction only along a subsequence, for example. And similarly here, if you have LP convergence, then it follows convergence in probability, but almost true convergence and LP convergence, they're not really ordered. So you cannot conclude LP convergence from almost true convergence, and also not the other way around. We have something here, uniform integrability, which you do not know, which we have to learn. And the V convergence stuff comes later in chapter 9. I will come to that back. So let's start with some definitions. So I have random variables in a metric space. So if it's easier for you, you can read R of x and y as absolute value of x minus y if E here are the real numbers, for example. And then we have these 3 kinds of convergence, which are these 3 here, because the convergence comes later. Almost sure convergence. So x1, x2, and so on, that's a sequence of random variables. It converges almost surely to x. If this here holds, so the limit rxn and x equals 0. So of course, what I would have to write down, the set of omega, such that this here holds, is 1. That's what I have to write. But usually I never write small omegas, but that's always what you have to keep in mind, and how all this is meant. And I will also write, if this here applies, that xn goes to x, and here is an arrow, that's from still the German version. That's an AS for almost surely, and not FS for fast sicher. Converges, okay, there are 2 notions here, which I will both use. It's going to stochastically to x, or in probability, I also say. So what does convergence in probability mean? That's the following. Choose any non-negative epsilon, or any positive epsilon. Then the probability that x and an x differ by more than epsilon goes down to 0, no matter how small epsilon is. And because here's a p in probability, I'll write xn goes to x and write an index p at the arrow. And last, the LP convergence. That's, I think, rather easy to grasp. You make xn minus x. You make this to the power of p. You take the expectation, and if that goes down to 0, then you have LP convergence. Okay, so yeah, several simple things. For example, if you have convergence in LQ, so this here, convergence in LQ to x, and p is smaller than q, then I will show you that then xn goes to x also in LP. If it should do this, I have to compute xn minus x to the power of p, which is xn minus x to the power of q to the power of p divided by q. And since p divided by q is smaller than 1, the function which maps x to the power of x to the p over q is concave. Yeah, so remember here, if p is equal to q, if I have done something like this here, I have that p is bigger than q, and I have something like more square root, then p is smaller than q. And such a function here is concave. That's concave, which means when I use the Jensen inequality, that here is smaller or equal than the same expression, but when the p over q is outside the expectation. And this here goes to 0, because by assumption I have xn goes to x in LQ, so this here goes down to 0, and the power p divided by q, well, that's continuous, so okay. Then LP is complete. Remember what is complete? Complete means that all Cauchy sequences converge. And I will rely here on your knowledge from measure theory, just give you what it means. If you have epsilon given and you find n and m such that this here is smaller than epsilon for every n and m bigger than some big N here, like this, and then there is an x such that xn goes to x in LP. So that is what is meant by completeness. And that's true for these LP spaces, which I'm not going to explain too much here because I rely on your knowledge from measure theory. Let's give some examples. Well, let's give an example here. So examples and counterexamples. So what do we have here? I have u equals is uniformly distributed. Here's 1. So uniformly distributed. So so u is a uniform value somewhere here. And xn equals 1 if the uniform distribution is in an and 0 otherwise. And what do I have here? Maybe I should draw it like this in different colors. So A1 is the interval from 0 to a half. A2 is the interval from a half to 1. Then I have the interval from 0 to a fourth. Then from a fourth to a half. Then from a half to 3/3. Then from 3/3 to 1. And so on. The point is that the intervals become smaller and smaller in length, which means the probability that u is in this interval, well, I can compute this. The probability that u falls in this interval here is a half, then falls in this interval here is a fourth, and so on. So that goes down to 0. Which means the probability that xn is smaller than, is bigger than epsilon for some epsilon bigger than 0. And maybe I need also that epsilon is smaller than 1, otherwise it doesn't really make sense. So let's take epsilon between 0 and 1. Then this here is the same as xn equals 1, which is the same that u in an. And since the an's become smaller and smaller, this here, as n goes to infinity, goes down to 0, which means that xn goes in probability to 0. On the other hand, let's look at almost true convergence. So for almost true convergence, we would have to have that the probability that xn converges to 0 equals 1. That's what we have to need. That's what we would need. But that cannot be the case because, also that's a question mark here. So that's a question mark. No. Question mark, right? But I claim that the lim sup of xn, n goes to infinity, is always 1. And the reason is the u that you have here has some value. Let's say like here. Then the intervals, so 0, a half to 1, they become smaller and smaller, but for no matter how small the interval is, you will always find some which with a bigger index which hits the u. And if it hits the u, then you again have a 1 in your sequence of xn, and that's the reason why lim sup xn equals 1, so that it cannot converge to 0. So xn does not go almost truly to 0. Okay, that was the one example. And the other example, it's similar. So that's a similar example. The setup is the same as in the first example, but the randomers are different. Here I have intervals bn, and they are different. So here b1 is the interval from 0 to 1. b2 is the interval from 0 to a half. b3 from 0 to a third. b4 from 0 to a fourth, and so on. So it becomes also smaller and smaller, but it's not true that these run through the whole interval. They're just here starting from 0. Another difference in this example here is that I do not take only the indicator function of Bn, but n times the indicator function of Bn. And that has a consequence. Well, so first of all, the probability that xn goes to 0. When does xn go to 0? That's the same as the probability that u is bigger than 0, because if u is any number bigger than 0, then the u is not in any Bn for n large enough, and then yn is 0. Sorry, it's yn, not xn. Yn is 0, and it just stays there. So that's the first thing, which means yn goes almost surely to 0. But so it's an AS, of course, again. Does it also converge in LP? And the answer is no. Because, well, this here would have to converge to 0. And let's take p equal to 1. Let's take p equal to 1. So what is this? The expectation of yn. So that's the expectation of yn, because yn is non-negative anyway. And this here is n if u is in Bn. So n times p u in Bn. The probability that u is in Bn is 1 over n. N times 1 over n is 1. Which means this here does not go down to 0. Which means that it does not converge in LP to 0. So we have here two examples. The first one, we have convergence in probability, but not almost surely. And in the second, we have convergence almost surely, but not in LP. Okay. So, last thing for today. The almost sure limit is unique, at least almost surely. Is the limit in probability also unique? So I have xn goes in probability to x and also to y. Is then x equal to y almost surely? And the answer is yes. And the proof is as follows. I have to compute that the probability that x does not equal to y, that must be 0. And I can do it like this, for example. That's the probability that there is some k such that the difference of x and y is bigger than, let's say, 2 over k for some k. This one here I can bound from above, so change the union by the sum. Okay, p r x y bigger than 2 over k. And then I can say, well, if this difference here is bigger than 2 over k, it must be that either the difference of x and xn is bigger than 1 over k, or the difference of y and xn is bigger than 1 over k. And this here holds for all. that holds for all n, of course. That holds for all n. And for this reason, it also has to hold for the lim sub n goes to infinity. And then must not forget the k here. Well, but this here is 0 because xn converts in probability to x. And the lim sub of this here is also 0 because xn converts in probability to y. So that's the sum over zeros, which is 0. And we have shown that the limit in probability is unique. Okay, that's it for today. And next time we will continue with convergences. Almost sure and in probability. See you then. Bye.